Okay, in today's segment, we are going to be looking at one important algorithm design technique or paradigm, which is called divide and conquer. So, the basic philosophy of divide and conquer can be split into three steps: divide, conquer, combine. So, the idea is when you are given a big problem to solve, you first break it down into smaller, non overlapping sub-problems of the same kind. I will explain this point in a little more detail shortly. So you break it down, you solve those smaller sub-problems individually, and then you combine the solutions of those sub-problems to arrive at the final solution to the big problem. So I will go back to the divide step and I'll explain some of the terms used there. So the slide says divide the problem into smaller non-overlapping sub-problems recursively. So when you look at the divide step of any divide and conquer based algorithm, there are two factors you need to keep in mind while designing the division. So when a problem is given to you and you decide that you want to apply divide and conquer to it, you have to define in what way you are going to divide the input given to you. And while defining that division, there are two things you need to keep in mind. The first thing is the sub-problems should be of the same nature as your original problem. The sub-problems cannot be something else. So for example, if the question given to you is to sort an array of integers, you can divide that array into smaller subarrays, but the task should still be sort those smaller subarrays. You cannot divide it and say I want this array to be transposed or something like that. So the task to be performed on the sub-problems should be the same as the original task given to you. That's one point. The second and more important point is the sub-problems should be non-overlapping. What I mean by non-overlapping is, one, they should be working with completely different pieces of data. There should be no shared data between them. For instance, coming back to our example of sorting an array, if you are going to split an array at the midway point, all the elements to the left of the midway point are one array and everything to the right is another array. So there is no common element. Of course, the same number might occur at two places. In that sense, you may have a common element, but no index as such is common between the left and right half. So the left half has the indices 0 to n by 2, for instance, and the right half will be from n by 2 plus 1 up to n minus 1 or n whatever. So the data units that your sub-problems are using should be mutually exclusive. Their intersection should be null. That is one point. That's one point which defines non-overlapping. The second point being, the solution to one sub-problem should not depend on the solution to another sub-problem. So if you take your array sorting example again, we had an array of size n. We split it into two arrays of size n by 2 each, which let us call left and right for the sake of simplicity. The task again is to sort the left array and right array separately, so the task is of the same nature. The array has been split in such a way that there is no common index, and the sorting of the left array is independent of the sorting of the right array, as in both can take place parallelly. There are no dependencies between the two processes. Now to contrast this, I will give you the example of computing, let's say, the factorial of a number. So if you want to compute 5 factorial, you need 4 factorial, and for 4 factorial you need 3 factorial, and so on. So now you can say the sub-problem is of the same nature, but it is not independent of another sub-problem. So for 5 factorial I need 4 factorial, but again for 4 factorial I need 3 factorial. Or if you take your Fibonacci numbers, to compute the 5th Fibonacci number you need both the 3rd and 4th, but again to compute the 4th Fibonacci number you need the 3rd. So there is an overlap or a sort of dependency between the sub-problems being created. That is not allowed in divide and conquer. So to summarize the divide step, you are given a large input, you are going to break it down into smaller inputs. A few things you have to keep in mind are, one, the smaller inputs should also be subjected to the same task which you were actually given the larger input for. 2, there should be no shared data instance among them. And last and final point, there should not be any dependency between the process of solving the individual subproblems themselves. So it's like you should be able to run the solution for all those smaller subproblems in parallel. So that is the divide step. You're going to divide your input in such a way that all these constraints are satisfied. Next comes the conquer step. So what happens is you first divide it, and then so let's say you had this array which you wanted to sort. You divided it into halves. You take one half, you again divide it into half. You take the half, you keep halving at every step until you reach some base case. So you see that we are repeatedly sort of performing the same action, right? Divide, divide, divide. So you might have sensed that there is some sort of recursion happening here, because you wanted to sort an array of size n. You divided it into two arrays of size n by 2, n by 2. Again you want to sort that array of size n by 2. So now you take that and again you are going to split it into two arrays of n by 4 each. Again the idea is you want to sort that array of n by 4 and so on and so forth. So because at every step only the input size is shrinking but the task remains the same, we can sense that recursion is involved in some way. And when recursion is involved, the first thing that should come to your mind is the base case. So the base case in most divide and conquer problems will be when your input is of unit size. It is an array of size 1 or a 1 cross 1 matrix, so on. Generally, not always, but yeah, 90% of the cases. So when you reach whatever your base case is, you will directly provide the solution. So that's what we mean by conquer. So if it's an array sorting problem, your base case can be defined as array of size 1. So an array of size 1, whatever the element may be, it is sorted because there is no comparison to make. So you will simply return that array. If it's a 1 cross 1 matrix, and let's say your question was to transpose a matrix or something. If it's a 1 cross 1 matrix, then again the matrix is equal to its transpose or inverse or whatever, so you will simply return the matrix. So in the conquer step, your problem is of the smallest possible size. So there is generally a direct formula to arrive at the solution. Sometimes the solution might be you simply return the element. Sometimes some manipulation might be required, but it is always a straightforward mathematically defined process. So you apply that procedure and you return the result at the conquer step. Now coming to the combine step, which is usually the trickiest step in any divide and conquer technique. You had a big problem, you divided it into parts, you divided, you reached the base case, you got the solutions. Now how do you put together those small solutions to reach the solution to the actual big problem? So this is where some logic will be involved depending upon what the question says. So if it's your array sorting problem, which we will be looking at in detail in a few minutes. So you have two sorted subarrays, you will perform something called a linear traversal and you will merge them both, and finally you will get a full array which is also sorted. So to summarize the basic philosophy of divide and conquer, you're first given a big problem which you will divide into smaller non-overlapping subproblems of the same type. You will keep recursively dividing till you reach the base case. At the base case you will conquer, you will solve the smallest version of that problem and you will return the answer. You will combine those answers to form the solution to the, let's say, the second largest input size. Again you will combine those solutions and you will recursively keep combining solutions till you reach the final solution for an input size of n. That is how divide and conquer works.